Make sure you type your questions in the chat window. Paul isn't going to be able to see them just due to his setup currently, but we are making sure that we send all of the questions to him so he will be able to answer them. So please make sure you type your questions in the chat window. Make sure that the icon at the top of your screen is green so that you are able to hear us. If you have any trouble connecting or if you lose your connection, you can email us at climatecampaign@globe.gov and we will be able to help you. So today's webinar is the final webinar in both the Student Climate Research Campaign webinar series as well as the Globe Data and Action series. And today's region that we are featuring is North America. So we are very excited to show our final region with you today. So just a brief overview of what we will be doing. I will overview the North America region, and then I will introduce our presenter and give the upcoming dates for the Student Climate Research Campaign. So, Globe North America is the region is composed of two countries, the United States and Canada. The United States was the first country to join the Globe program on April 22nd, 1994. Canada joined almost 3 years later on April 7th of 1997. And a fun note that I found out when I was researching their date, they were the 50th country to join the program, so they were a good milestone for the program. The region is represented on the Globe International Advisory Committee by Lynn Hare, and also has representation on both the Education Advisory Committee and the Science Advisory Committee. There are over 14,200 active teachers in the region, and they have taught over 340,000 students. The more than 18,200 schools have taken and submitted over 67 million observations to the Globe database. So they have provided a wealth of data to the program. Schools in the region also participate strongly in other aspects of the Student Climate Research Campaign, such as joining in competitions, like our art competition and our video competition. They also attend webinars and perform research projects and submit them to the Globe database, or submit them to Globe. So these are just some pictures of students performing research in North America. So to show how the region uses Globe data, we have Mr. Paul Hamilton with us today. He is a member of the Globe International Scientist Network. He is also the curator of the National Phycology Collection of Canada, which is a part of the Canadian Museum of Nature in Ottawa, Ontario, Canada. His primary focus, phycology, is the study of algae. The collection that he works on began officially in 1996, but the first specimen was collected in 1882. So this is a very long-standing collection that they have there. And to date, the collection has over 84,000 samples. So it's a great pleasure for me to welcome Paul Hamilton, and he will take over and show Globe in North America. So go ahead and take it away. Seems like we're having just a problem with his microphone, so give us just a second.
Okay, I think I'm there now.
Yes, you are. All right, take it away.
Sorry about that. Okay, so what I would like to do, share screen again. Sorry. What I'm trying to do today is use Excel as a way to make this communication. So it's going to be a little bit, so it's an ongoing kind of thing. So I hope you can see my screen at this point. And what I have is sort of an outline of where I'm going to go with this presentation. And so I'm going to start with looking at the tools for looking at temperature data through time. Then I'm going to flip over and start talking about time scale and how important or not important time scale is with respect to trying to interpret the data that we do have. And then I'm going to sort of end off with some quick examples of some hypothesis testing over a longer period of time with a larger data set. So I'm hoping to progress through here to give everybody an idea of how you would go about looking at your data, the kinds of questions you would ask about your data, and the kinds of caveats or problems that you may have along the way with the way you're presenting the data. So, to get started, I'm just going to quickly talk about making a graph. I'm sure you all know how to make a graph in Excel, but I'm just going to go over it anyways just so that we're all up to speed. So, when I've selected a set of data points, in this case I've selected time and temperature, you can see highlighted on the left, then what I will do, of course, is make a line graph of that. And what you have to the right over here is a line graph of the data that's on the left-hand side. So for the rest of the presentation, that's what you're going to be seeing is the data on the left-hand side and the graph of the data on the right. So the question becomes, how do you interpret the graph that you're seeing in front of you here? There's different ways of doing it, but the one way that we traditionally use is called a trend line. So I've right-clicked on the mouse, and up comes the pop-up and for you to put things into or add to the data set. And the one kind of thing that you want to use in this case is called the trend line. And so from this point on, for the rest of the presentation, we're going to be talking about trend lines. So I've just clicked on the mouse, and these are the kinds of trend lines. I'm just going to move this over to the right so you can see. So as we have right now, we have a black line here showing a linear trend line through the data set. As you can see, it's not very, very helpful in this case. So I'm going to switch and say, well, let's take a look at the log trend line and see what it does. Well, a log trend line isn't really all that helpful either. But now let's try maybe something called a polynomial trend line. And then you can change over here in the right, just beside the polynomial, you can change the order of the polynomial. Notice as I'm changing the order of the polynomial, the trend line starts to look like and become more similar to the actual data. So this polynomial is a very good tool for trying to map our data set against time. Let's try a power line. Power line is not very helpful at all. As you see, it's not even visible at all. And then finally, moving averages. Moving average is a line where you take 2 points, one beside one temperature point, and then to take the next temperature point the next day and average those and then present that as the data point. And if I go to the right here and I click and I increase the number of average data points, so in other words, 3 days are averaged together and this 5 days are averaged together before I actually put the data point, you can see that a trend line starts to mimic the temperature data, but notice how the line is offset from the temperature data. That's typical of what we call a moving average. So those are the basic things. Now what I'd like to do is to switch over and start looking at some real data. Here is this. Get this out of the way. Here is some temperature data from Heartland, and Heartland is over here. It's sort of the northeastern part of North America, and this data represents basically about a year and a half of temperature data. What we've plotted up, so I've just taken the numbers just like we had before, and I plotted up solar noon temperature data through time. And in the bottom graph here we have maximum temperature, solar noon temperature, and minimum temperature. What I'm going to do, just like I talked about before, I'm going to right-click on the mouse, I'm going to add a trend line, and I'm going to start, and notice the linear regression line, that black line is terrible, it doesn't help us at all. The log line, as you remember, isn't very helpful at all, but the polynomial, remember, should work. So let's increase the polynomial, and look at that. A 3-order polynomial will actually give us a very, very good link to the trend line. So for short-term data sets of a year or 2 or 3, potentially a polynomial is a very good line to use to try and get an idea of what your data is about. And if I do then look at the bottom here, I did display the equation, and if we look at the equation then and bring, grab that. We can start to look at the equation and the significance of that line in terms of explaining the temperature data. So polynomial is a very, very nice tool to be able to do that for short-term data sets. Okay, so let's now switch over to look at Lowry Elementary School. And Lowry, oh, sorry, I should have done this view full screen there. How's that? The Lowry School is down in central United States. And in this case, we have 1, 2, 3 years of temperature. And again, I'm going to go through the same process. I'm going to right-click, add a trend line. And as you can see, as you know from before, the linear trend line is not very good. Let's go to the polynomial, and I'm going to increase that. And notice the polynomial is starting to get better, but I max out at 6 orders of polynomial, and notice the polynomial does not work. So a polynomial can work for short-term data sets of, let's say, 2 years or so. Anything more than 2 years, a polynomial becomes a problem because it will not mark the trend. However, we can use something called a moving average, which is the bottom one here. The black line that's overwritten the blue temperature data line is the moving average. And what I'm going to do is increase the moving average, and I want you to watch the black line as it starts to change. When it starts to change, it becomes more, as we average more temperature data points together, the line starts to smooth out, and the line becomes we're at 22, averaging 22 data points at this stage, and you can start to see that basically a moving average is a good way to track temperature over 2, 3, 4, 5, 6 plus years. So now we have a scenario of we need to understand our data and the length of time that we have for our data set. So now I'm going to switch over to Winnetka Field Station, the next one over. And in this case, we have 1, 2, 3, 4 plus 5 years of data. So this is getting to be quite impressive. We have a good data set. I'm going to run through the same process again. Right-click the mouse, add trend line, linear trend line, maybe not so good. Polynomial trend line, remember I said doesn't work at all. Now I'm going to the moving averages, which is at the bottom here, and I'm going to increase the number of data points with the moving average, which smooths out. So the moving average can work out very, very well. And for longer data sets, notice that the offset isn't that bad, so that there is potential to be using a moving average. However, having said that, one of the questions that we ask with larger data sets is, in this case, for Winnetka Field Station, is the temperature getting warmer over time, over a longer period of time? And so to do that, I hate to say it, we have to go back to a linear regression, because that linear line can tell us whether the peaks and the valleys over time are actually starting to change. Are they starting, the overall trend is to go up, or the overall trend is to go down? So for better for worse, when we have long-term data sets, we are pretty well stuck with using a very simple kind of a relationship, which is usually a linear relationship. And I'm going to show you an example of that later on. So what I'd like to do is to get started by looking at the comparison of the schools. So here we have the 3 schools. I put them in shades of gray just so that they don't make it really messy. So we have the 3 schools down here. So we have the 2 from the northeast, the Field Station, Winnetka, and the Heartland, and then we have Lowry down in the central United States. So I plotted the lines. Here's the data on the left-hand side. We plotted the lines, and you can see that the temperature data is all over the place. Because it's only a 1 year plus data set, I've applied the polynomial lines, and here are the regressions for each of the polynomials. I've colored them so we can get an idea of what's the trends, And so my question to you at this point, and so please answer, is there's two things that come up from this graph that are statistically significant. Can you tell me what one or two of those things are? Please go ahead and answer. And I'll just say that what you're looking at is the relationship between the lines as they change through time. Okay, the question is, there's two findings, or there's two results from this graph that are quite obvious, or fairly obvious. And what I was asking was, can anybody tell me what those two relationships are? Or at least one relationship anyways. And so what you're doing is you're looking at the relationship between the polynomial lines as they pass through time. How does that sound? That's correct. So central U.S. is warmer. The blue line is definitely higher. There's one other thing that blue line, look at the relationship of or the distance between the blue line, i.e. central United States, and the northeast United States. Look at the distance between those lines as they travel through time. And so the second finding is, if you'll notice, is that the lines are close together over here during the summer season. As it goes, temperature develops into the winter season. Notice that central United States stays warmer, exactly, than the northeastern United States. And then as the summer comes back together again, they start tracking together again. So these are some nice things that we can do very easily using a polynomial and starting to compare temperature data sets for periods of time of 1 to 2 years. And we can effectively get some very good results, some very good answers and results. So, sounds good. I think, does anybody have any questions at this point? Because I'm going to take a leap to some hypothesis testing now. So I'm not seeing any questions, so I'm going to move on now and start going to the next step, and that's talking about hypothesis testing. Okay, perfect. And so some of the things that we think we know that climate warming has been happening over the last 15 years and can be observed in North America. So people say that all the time. But the question is that real? Can we really track warming temperatures over the last 50 years in North America? So that's the first hypothesis we're going to test. The second one we're going to test is climate warming more evident in the north compared to the south? So in other words, remember we just did an example where we looked at temperatures from central United States and a temperature from the central United States and from the northeast, and there was a difference. Now my question is the warming in the north faster than warming in the south? So to do that, there we go. I've constructed a temperature set. First, I'm going to first of all describe the graph. So the top graph here with the blue dots represents a point up here, which is the top of Ellesmere Island, which is at the top of Greenland. It's a temperature data set that started in the 1950 over here to the left and goes all the way to present day, but I only have to 2010. So we have a very, very good temperature data set. We have winter temperatures, we have summer temperatures, we have daily temperatures, monthly temperatures, and that data is all available, and I can give it to you if you want to start playing with good large data sets. The second data set down here, a place called Iqaluit, which is the capital of Nunavut, the Northern Territory of Canada, is this green dot over here, which is basically down towards the bottom of Greenland and in north central Canada. Again, we have temperature data. For comparison purposes, I have temperature data that goes back from 1950 up to 2010. Finally, I have the capital of Canada, Toronto, which is down here in the red dot, which is very, very close to the two schools in the northeast United States. And to make everything match, I've selected the temperature data from 1950 to 2010. Temperature data for the city of Toronto and for a lot of cities in North America can go over 100 years. But for the purposes of this hypothesis test, I've only selected the last 55 years of data. So, remember when I talked about if I were to plot, well, why don't I do it? Oh, no, I can't. Actually, I can't do that. Or can I? No, I can't. Because I just copied the data sets over. Anyways, what I have here is I have the linear regression line, which is a straight black line. And the second line is I have the trend line. So and the average, this is doing the moving average calculation. And the temperature, as you can see from here, is the average summer temperature. So I've chosen the summer temperature because of the Arctic. The theory would be that the summer temperatures are going to get a lot warmer, a lot faster. So that's why I've chosen summer. And to match up everything, I've used summer temperature all the way through. So we have a running trend line for averaging, and we have a linear regression line. Notice it's very, very difficult to try and compare the running average trend lines with each other. It's extremely difficult to compare. It can be done, but you have to use some very interesting mathematical modeling to do that. The linear regression line is an interesting one, that black straight line here. So that regression line, or that straight line, basically tells us, on average, which over the last 50 years, how has the temperature been going? In the case of Alert, the north, the temperature is actually slightly declining. Over here is the temperature on the left-hand side. So the average summer temperature is in around 2.5 degrees back in 1950. And then today it's probably about 2.2 degrees. So Alert, the furthest point to the north, is getting colder through time, we think. Iqaluit, which is over here in sort of the bottom of Greenland in central Canada, the trend line suggests that the temperature is getting warmer. Slowly, but getting warmer. And finally, in the case of Toronto, which is down at the bottom here, the trend line is again increasing, which tends to suggest the temperature is getting warmer. In the circles here are the regression line calculations and what they call the R-squared, or the significance of these lines, the relationship significance. And I just tell you that these relationship significance are extremely poor. So, in the case of Alert, the temperature is going down, at least we think it's going down slightly, but the relationship is extremely poor, and it's very, very hard to tell whether it's actually going down or whether it's staying the same. And the case of the same for the Iqaluit and Toronto. So the regression line analysis in these data sets is a little bit difficult because of the fact that the lines are not really strong relationship increases, which, by the way, is typical for most temperature data. So my question then, in this case, is because we've made this hypothesis test to say that the temperature in the north, which is Alert, the top up here, is actually changing faster and increasing faster than Iqaluit, than Toronto. So based on what you see in these graphs, I want you to answer yes or no. Is the temperature getting warmer in the Arctic faster? Yes or no? Exactly. So based on this data set, perfect, thank you. Based on this data set, not only is the temperature not getting warmer, it's actually staying the same or getting colder. The next question that I had was, is the temperature, so it's not getting warmer faster in the Arctic. The next question I have is, and again it relates to the one I just finished, and that is the relationship or the degree of the change happening faster or not as we move north? So in other words, is that linear line, in the case of alert, which is slightly going down, is it going down faster, or is the slope of that line greater than the slope of the line? This line here, is the slope of that line greater, either going down or up, compared to the slope of this line, which is Toronto, going down or up? So my question, is the slope more or less than the slope of the Toronto line, more or less? Yes or no? Perfect. Thank you very much. Those are exactly correct answers. Not only is in the case of the alert, the slope of the line going down, which we didn't expect, the actual degree of the fall going down is a lot less than the degree of the slope going up for Toronto. So that tells me that, yes, there's the temperature in Toronto, in this part of Canada, is actually going up to some degree, but the north is not. So the north at this point in time is not. So my question to you, and I'm hoping to put this into the discussion forum if people want to contribute after or through the next week or so, is A, why is the north temperature getting colder or staying the same? It's supposed to be getting higher. All the models say it should be getting higher. So what is it about this site alert which maybe is causing the temperature not to get higher or colder? And my next question is, why is it that that the Toronto, the Southern Ontario one, seems to be getting warmer faster? So those are two things I'd like to pose later on. I'm going to finally finish off with a point, and the point is, we just finished showing you here 50 years of temperature data, and it's not convincing. I think you'll agree with me that it's not very convincing whether the temperatures are going up or down. So in order to determine climate change, we have to go and actually look at longer periods of time even. So 100 years or 50 years is nice if it's very distinct, clear change. But in the case of what we just looked at, it's not that clear. So we need to go beyond 100 years, beyond 200 years. And the problem is, of course, we do not have temperature data going beyond 200 years. So we have to use something called proxy data. So we have to go back and look for clues, fossils. And the fossils could tell us a little bit about what the temperature was like in the past. So I'm basically a climate reconstruction researcher using microscopic organisms because there's lots of them and they change through time. So this is one of my study sites, which is in the middle of the Arctic. Here's Greenland over to the right. This is the top, that's alert, that top station. This is the middle of the Arctic. Toronto's way down here and the United States is down below. At this site, we took a core from the bottom of a lake. And what you have here are as an X-ray of the mud from the bottom of the lake. And you notice the nice layering that goes on all the way down through this whole sequence. This represents, it goes down to here, then it comes back up and around. This represents about 7,000 years of history. And if I could look through this section of cores, and I can find my microfossils, which are things like the diatom shells that I'm showing over here on the right-hand side, then I can turn it around and I can use this diatom shell or these algae to predict what the temperatures were like in the past. And so by doing that, I can reconstruct the theoretical temperatures over the last 7,000 years. And we have done that, and we've published a number of papers on it. But in a nutshell, what I could tell you is this, or in a summary. Over the last 50 years, which is this little section, this little bit of mud right up here, for the last 50 years, the climate has changed faster and stronger than any other period in the last 7,000 years, which means through all the rest of this history, the most significant change in the algae that we're growing and the number and the types have all been up here in the top of this section, which is right up here in that little bit. So my final point that I want to make it before I open it up for some questions is we do need to go longer term if we will have specific questions that we want to talk about. Good. I'm still connected, I hope. And so we have a longer period of time that we need for asking those kind of questions. And the second point I'd like to make is that when we use temperature data, if you understand the degree, the time that you have, good, thank you for responding. when you use temperature data, you must understand the length of time that your temperature data is before you assign your analysis. So just as a quick summary, if we go back to the Heartland graph, short-term data sets of basically trendline, the polynomial works very well to recognize the data. Longer-term data sets, the polynomial doesn't work so well, but if we use what we call a running average trend line, the moving average or running average, it does a very good job of tracking temperature changes through time. That's fantastic. However, if we go to a longer-term data set, then using a running average cannot help us to try and determine whether the temperatures are getting warmer or colder. So therefore, we have to flip to starting to look at linear regressions. And then finally, I ended off with looking at hypothesis testing using these linear lines to try and get an idea of the changes through long periods of time. So that's my message today, and I'm hoping that we can maybe, if you're interested, continue with the discussion forum and talk about what's the problems with temperature data, why is it that the north here did not get warmer like it's supposed to, and explore some other ways that we can actually determine the changes. Remember, my core that I showed you actually showed that the temperatures up in this section right here of the Arctic were getting warmer faster than ever before for the last 7,000 years. But this point here is colder, getting colder, as that trend tends to suggest. So that's the dilemma I'm going to leave you with today. Thank you for participating and tolerating my rant about temperature data and climates. And as I say, I hope we can continue this in a discussion forum after the fact. Thanks.
Thank you so much, Paul. Does anyone have any questions? We can answer a couple here. We have just a couple minutes if you would like to. Okay, just another minute. Okay, Matt's question.
Yeah, please. Okay. You going to write it?
Yes, well, I can just speak it here. So he says that he is new to Globe, and he had to step away for a minute, so he apologized if he explained it.
They are, at this time, they're not, but I can make them available. Yes, so what I will do is, with your help, I will pull some of the data that I've been collecting and used in publications, and I'll put them, I'll give it to you to put on the Globe site so it can be used, which will also include some pictures to identify the different, some of the different organisms. And I can also give you supply a really crude but a very somewhat effective identification chart for these algae, so you can actually, by looking at some of the pictures, you can get an idea what they are. So I will do that.
That would be great. And then maybe we can write a blog post on it from the Globe Program Office, just saying that this data is available for students to use. Because I know that Paul is very busy. So we will work with him to get that information up. So thanks, Matt, for the suggestion. And we're going to go ahead and move on just because it is a little bit late. But thank you again, Paul, for sharing this wonderful presentation with us. I learned a lot, and I hope everyone did too. And we mentioned that the discussion is going to continue on the website. So I'm going to post a link to where we have the discussion set up. in the chat window, so be sure to head there and ask any additional questions and continue the discussion there, because this is a great, this is some great research that he provided and great examples for GLOBE students. So Paul, if you want to go ahead and stop sharing your screen, I will go back to our presentation to wrap up.
Okay. Let's see.
There we go. Okay. Okay, so some upcoming dates for the remainder of the SCRC. As you all are probably aware of, the Student Climate Research Campaign is in its final stages. In the final couple of months, excuse me, and there are still a couple of IOPs that students can participate in, and that is currently right now for the remainder of the month of June. We have the Great Global Investigation of Climate, as well as the Phenology in Climate, and so those are two great ways to participate. And then in July, we will have the Climate and Land Cover IOP to get outside and take photographs of your land cover sites. So those are three exciting IOPs that are still continuing. Okay, so other activities for the SCRC. On August 10th, we will announce the winners of the Virtual Student Conference. The research reports and videos for the conference are still available for viewing, and you're more than, we would love to see you still ask questions of these students. They may not be able to get back and answer them because in a lot of places it is break, but please go on there and check out some of the fantastic research that GLOBE students are doing. And you can access those by clicking the link at the bottom that says 2013 Virtual Student Conference. So please go and check those out. The GLOBE annual meeting is taking place at NASA Goddard from the 12th to the 16th of August. And along with that is the Student Research Exhibition, which is an exciting part of the annual meeting where partner-nominated student research is being presented. And currently there are 30 presentations from 8 countries participating. And so those are exciting things. And if you hadn't made up your mind to come to the meeting or not, this would be a great motivating factor to come and check out this research. Also, one thing that's not on this slide, but it's at the bottom under the web links as well, is the 2014 GLOBE Calendar Competition is coming. So be sure to check out that link. You can find out more information by clicking on there and finding out the details on that. So I want to thank you very much for attending the webinar today and for attending the wonderful SCRC webinars that have been presented by GLOBE partners and country coordinators throughout the last few months. I hope you've learned as much as I know that I have, and please continue the discussion on the discussion forums. Again, we linked the one here in the chat window that you can go to specifically with this webinar. If you missed any of the others, they are archived on our site, so you should check those out when you have some time. And if you have any additional questions, I'll hang on for a few minutes to answer those for you. Again, thank you so much for attending and participating in the Student Climate Research Campaign.